Hi, this is Karina Patel, and this is Physics 1 Lab 5. And for this lab, it was a DIY pick your own adventure type of lab, so I chose the Fallen Slinky video. So the purpose of the Fallen Slinky lab is to determine if the bottom of the Slinky will stay stationary in the model, like in the video. And so the computational model used was GlowScript, and then Tracker was also used to determine the position of the Slinky. And then the video for the Slinky was from some guy on YouTube. And then the physics principle used was Newton's second law, drag force, gravity, and then also tension force. It's not listed here. So the preview of the results, basically the bottom of the Slinky stayed stationary in the video and in the computational model, and that both lined up. There were some slight differences, but I will discuss in the error section why that might have happened. So the main physics idea used is Newton's second law, where we get the position update formula shown on the top and then the velocity update formula showed underneath that. And that's used to update the bottom of the Slinky's position over time. And the drag force formula shown on the right is also used. That's shown like the Slinky's movement in the air, its distance to the air. And then also it's important to note that the force of the Slinky is actually tension force, and that acts in the opposite direction of gravitational force. So the setup, the system is the Slinky, the surroundings are the drag force, gravity, and the tension force, basically from the Earth. And then the screenshots on the right are from the actual video. The screenshot on the left is when the Slinky was first released. The screenshot in the middle is when the Slinky was halfway contracted, and then the screenshot on the right is when the top of the Slinky finally caught up with the bottom of the Slinky. And then the initial time was 0.07 seconds, delta t was 0.03 seconds. So each snapshot from Tracker was taken in that interval, and then the initial velocity at the bottom of the Slinky was 0 meters per second. So this is a code. On the left, you can see the net force being calculated at the top, and then underneath that, the velocity and position update formula that I mentioned earlier. And so then this is comparing the results between the computational model and the experimental model. And as you can see, for both of them, the position of the bottom of the Slinky stayed relatively the same for about 5 seconds. And then after 5 seconds is when the top of the Slinky caught up with the bottom of the Slinky, and then it started to move downwards. And they don't line up perfectly, but there's some things that could explain this. So the possible errors that could have happened is that the measurement/data points could be inaccurate on Tracker. I had to manually input those, and Tracker is pretty old, so they could be a little inaccurate. And then the real-life scenario in the video could be experiencing other forces that are not accounted for in the computational model. Like possibly there was like wind or something that was not accounted for by the forces that I had in the code. So for the what does it mean and why questions, I kind of came up with some that could be appropriate for the lab. So for what does it mean, why does the bottom of the Slinky stay stationary? It's because the upwards force of the stretched spring tension perfectly balances the bottom downward force of gravity. In other words, to make this make more sense, the force in the y direction cancels out, so there is no movement in the y direction of the bottom of the Slinky. So this bottom of the Slinky stays stationary until the top of the Slinky catches up with it and forces it downwards. And then what if the Slinky is held and released horizontally? So in the video, the Slinky was released in a vertical direction, but what if the Slinky was held from side to side and then released? So the ends will immediately snap towards the center, causing the entire Slinky to contract longitudinally before falling to the ground. Unlike a vertical drop mentioned in our experiment where gravity is balanced by tension, a horizontal release will remove that vertical balance, making the whole object accelerate downward while simultaneously contracting inward. So since there's no tension force to balance out that gravity force, the object will accelerate downward and inward at the same time. Thanks for watching.